Hi guys, today we're going to do the problem LeetCode 104, the maximum depth of a binary tree. So let's read this problem and see what this problem is asking us to do. So we are given the root of a binary tree. We have to return the maximum depth. And it says that a binary tree's maximum depth is the number of nodes along the longest path from the root to the furthest leaf node. So if you look at this first example, they're asking us to find the length from this node, the root, to this node or to this node. Essentially, it is a value of 3 because you have 1, 2, and 3. So if we construct this particular tree on our whiteboard, then we have 3 out here, then 9, 20, 15, and 7. So 9, 20, and then 2 more nodes, 15 and 7. So now this is the input and our output is going to be an integer, which is going to be the depth, the maximum depth of this particular binary tree. And we are given some constraints where it says that the number of nodes can be in the range from 0 to 10,000. Node values are given out here, but they are immaterial because we don't really need to use them at all out here. There are a few more examples that have been given out here where you're given another tree which is 1, null, and 2. So that is 1, null, and 2. So that is this. So your height will be 2 in this case. And in case you're just given the node 1, then the height will be 1 out here. So now the approach that we're going to do is that of using recursion. So now what we're going to do is we're going to start from this particular node and increment a counter which starts with 1. Now we're going to go left and right and keep finding out the maximum height for both the left branch and the right branch. So here the height is going to come out to be 2. Here also is going to return 2. Then it's going to come here again. We're going to find the height of the left and the right branch. So we're going to get 3 from here and 3 from here. And then at every step, we're going to find the max of the left and the right branches. So between these two, it's going to come out to be 3. Between these two, it's going to come out 3. And then that 3 is going to propagate to the top and come out as 3. Similarly, for this case, we start here. We have a height of 1. We go here, there's nothing. Height returns as 1. We go here, height returns back as 2. And then max of between these two branches 2, so the height becomes 2. Here there's no question because we only have a root node, so the height is 1. And then remember that in case we are not given any node, the height is 0. So that will form the base case. So now let's start coding this problem. And as always, since we're using recursion, we need a base case. Otherwise, the recursion is going to go on forever. We need the recursion to stop. So first, we need to check for empty root. If the root is none, return 0. Next, we have to check the height of the left subtree. So I'm going to declare a variable called maxL, and I'm going to call the max depth function here with root.left And I'll repeat the same thing for the right subtree. So I'm just going to copy this, just make it as right. Put that as right, and then make this as R. Right? Now, here we need to find the maximum of the left subtree and the right subtree. So the way to do this is that we have to return the max of both these variables plus 1 to indicate the height, or to indicate the root of that particular binary tree. Now let me just run this code for some examples and see if it works. So I simply run this code for this particular test case, which is what we saw here. The height comes out to be 3. I'm going to try with other test cases, such as this one. The answer is 2 here. How about where you only have the root node? Answer should be 1. And then if there is no root node, answer should be 0, which is essentially this. So now I'm going to go ahead and submit this. Now when we submit it, our solution has been accepted. Now the time and the space complexity for this particular problem is that if you go back to the whiteboard and look at this example, so the time complexity is that we have to essentially visit every node out here. So since we're doing that, our time complexity is going to become O of n, where is the number of nodes. And the space complexity is going to become the height of this particular tree. Because at any point of time, if we look at our recursion stack, we're going to have the height number of nodes. So that's the reason why the space complexity is going to be height. Now, this also depends on what we're using. So in case there are so many nodes, then the height will become the same as O of n. So our space complexity is going to become O of n in this case. So that's all, folks. Thank you so much.